Okay, so anyways, welcome. My name is Professor Miller. I'm one of the professors who is leading the Number Theory and Probability PolymathJrREU group this summer. That is a big mouthful. We have another colleague on board who is here today. Can you just quickly identify yourself?
Hi there, my name is Dr. M. Tip, and I'm the also the academic director. But I'm also this is my first time here, so I'm assisting Professor Miller here to do it.
And so the way we run our group is a little bit different than a lot of the other groups in Polymath. And what we do is we actually break the probability number theory group into subgroups. And so there are 5 of us listed here. There may be another 1 or 2 former students who are going to join and help with some of the Zeckendorf problems. And what I want to do today is just talk very briefly about my philosophy and then about some of the possible problems you could look at this summer. So I'm a huge fan of what's called the law of the hammer. And there's a lot of different variants and ways of phrasing it. One of my favorite ways is the last one. If all you have is a hammer, everything looks like a nail. There's a couple of ways to look at this. One way is that if you're really good at something, you take whatever you're given and you find a way to look at it so that you can apply your expertise. If you're really good at integration, you try to make this an integration problem. A better way of looking at this is, what is your competitive advantage? Why do you think you're going to succeed at a problem where others can't? And if you have the same training as everyone else and you're looking at the same problems, it's hard to really shine and distinguish yourself. But if you go to the land of the screwdriver, there's smart people there. If they could have solved it using their tools and techniques, they would have. If you have a different tool set, if you have a hammer, you have the ability of making a real contribution. So I've worked on problems in a variety of fields, from accounting, economics, marketing, statistics, physics, computer science, all over the place. And what I would like to propose for this summer is 5 general areas. 2 of them are pretty similar. I'm going to talk about generalizing the M&M game, and this is a great example of showing how you can find research problems almost anywhere. And then my colleague will talk a little bit about God's number for some Rubik's Cubes. For the other ones, you can read the stuff online. But what I hope you'll get, without even going through all the details of that, because you only have so much time, is just a flavor for how we want to do problems here, how we want to try to find research areas that are going to be of interest that can be split into lots of sub-problems. So whoever's working on it will have some area where they'll have a sense of ownership. So this is the abstract from the paper. You should have seen this on the Polymath wiki page, so I'm not going to go through this again in great detail. This was inspired by something when my son was 4 years old. He asked me, if you're born on the same day as someone, do you die on the same day? Well, my wife's an identical twin. I don't get along well with her sister. All of a sudden, if my wife's twin sister is gone, look, mom's still alive. Well, obviously there would be issues if we did something like that. That is not a good way to explain randomness to a little kid. So what I did instead is I created what we call the M&M game. And so my son, daughter, and I, we each took 5 M&Ms, and we each took a coin, and we go 1, 2, 3, toss. And if you got a head, you ate one of your M&Ms, and if you got a tail, you didn't. And we would say you died at the same time if you ran out of M&Ms at the same time as someone else. So this is a really simple game. We played this a couple of times, and quickly it became apparent that even though you started at the same level, it was rare for people to die at the exact same time. Well, how rare is it? What's the probability that everybody dies, or if you have 2 people, that 2 people die? How does it depend on the number of M&Ms? And it turns out, there's, again, lots of questions you can ask. What if there's more people? What if the coin is biased? Lots of things you can do, and we can analyze these completely. And so, whoops, went forward 2 slides. So here is a plot of the probability of a tie as a function of the number of M&Ms. You've probably heard the phrase, a picture's worth 1,000 words. This one is probably worth maybe 200 to 300. It's not so easy for me to look at this and see what's going on. It's hard to predict what happens next. So a big thing is trying to figure out, once you gather the data, which is extremely important for problems like this, to get some sense of what might be worth conjecturing, and if you have an idea of what might be true, that can guide the proofs, you want to present the data in a useful manner. A logarithmic transform of the data is often very useful. So rather than plotting the probability of winning against the number of M&Ms, we plot the log of the probability of a tie, against the log of the number of M&Ms. This should not be a difficult shape to point out. If you look really closely, you can see, let me see if I can zoom in, you can see that there's a little red line going almost perfectly through the center of the dots. And we can use this to use what's called the method of least squares or linear regression to find the best fit line through the data. And we predicted that for 220 M&Ms, the probability of a tie is 0.01344. The correct probability is 0.01347. That's pretty good. For small amount of data, just looking at 60 values from 50 to 110. So as I said, this uses a lot of great mathematics. What's looking? Memoryless processes play a role. Catalan numbers, if you've seen them, play a role. Hypergeometric functions play a role. So again, starting with a very simple question, a lot of interesting mathematics quickly enters. So where does this leave you? Well, I like to view problems like this as a springboard to great mathematics. So here are some possible problems we could look at. What if each person has a set of coins of different denominations that they toss together? Maybe the coins are different powers of 2. Maybe the coins are Fibonacci numbers or in arithmetic progression. How is that going to change the probability of a tie? What if some coins have positive and some coins have negative amounts? What happens if you're in higher dimensions? You have a walk on a lattice. So these are just some of many questions you can do for a game like this. What I love about this project is the mathematical prereqs is very low. And for those of you who are just joining us right now, don't worry, everything is being recorded and we're going to post the slides later. So again, for a problem like this, very easy to state, a 2-year-old and a 4-year-old had no problems figuring out what was going on. But figuring out what the answer is, figuring out nice closed form answers for the probabilities ends up involving a lot of really interesting mathematics. So if you look at something like this, you'll see a lot of good advanced mathematics, and you'll have a lot of opportunities to be creative in determining which direction should we go. I want to just briefly mention the Zeckendorf game before we go over to Rubik's Cubes. And so hopefully everybody has seen the Fibonacci numbers, where each number is the sum of the previous two. There's lots of ways to define them. I'm going to define them as 1, 2, 3, 5, 8, 13. So the reason I'm not going to have 2 1s or 0, 1, 1 in the beginning is because this way we have what's denoted by Zeckendorf's theorem, even though he was not the first to notice this. Every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. The proof is not that bad, but with just 20 minutes, I'm not going to go into it. I'm going to just show you, here's a decomposition for 51, here's a decomposition for 83. We can use this to create a new game called the Zeckendorf game. So we take 2 players, they alternate, last one to move wins. You start off with n pieces on the first Fibonacci number, 0 on the second, 0 on the third, and so on and so on. And on your turn, if you have 2 pieces on one bin, you can remove and put 1 piece on the next bin and 1 piece too earlier. So if I have 2 8s, I can replace that with a 13 and a 3. If I have 2 13s, I can replace it with a 21 and a 5. You have to be a little bit careful if you're around 1, 2, or 3. I'm not going to worry about that in a quick 5-minute introduction. The other move you could do is if you have 2 adjacent Fibonacci's, something on the 8 and something on the 13, you can replace that with something on the 21. And here's an example of how one game might go. So I'll start off with 10 pieces on the first bin. The only possible thing I can do is I can take 2 of them and put them on the second. And note, 8 times 1 plus 1 times 2 still adds up to 10. What I'll do is I'll take 2 more on the 1 and put it on the 2. And now I can split the 2 1s on the 2 and give me something back on the 1. That's why this becomes a 7, and something on the 3. And so on and so on and so on. And it turns out you can show by introducing something that's called a monovariant, which I'm not going to get into right now, you can show that every game is going to terminate. It will terminate in finitely many moves. It can even bound how finitely many, and it will terminate in the Zeckendorf decomposition. And you can use that to show that there is no way of writing a number as a sum of Fibonacci numbers that uses fewer summons than the Zeckendorf decomposition. We were able to come up with a non-constructive proof that player 2 always has a winning strategy if n is at least 2. It involves a nice parity switching strategy. There's a lot of related questions that I believe are accessible. I would love to see a proof that player 2 has a winning strategy that is constructive. I will give $500 to anybody who can do that. If that's not enough money, I'm willing to go up to 1,000. Extremely hard problem. Even special cases are difficult. But we have a lot of related games where things are interesting, where you start off with the Zeckendorf expansion, you try to run backwards. And so again, the goal here is to take something that's very accessible. You don't need advanced mathematics, you don't need graduate classes, but you need to be creative. You need to find what's a good thing to study And like the other problem, there's a lot of sub-problems here, so we can split into lots of smaller groups and give everybody, a sense of ownership. So at this point, I'm going to turn the floor over to one of my colleagues who will talk about God's numbers for the bicolored pocket and standard Rubik's cubes. So I will let you share your screen.
All right. All right. Thank you, Steve. Let me see here. Yep. All right. So here is my project here. Yes, I am a very big fan of Rubik's Cubes and any mathematical toy in general. And I'm similar with Steve. It's just like, let's kind of do something very kind of easy for you to start off with not required, but can get a lot deeper in mathematics wise. Okay. So, okay, let me kind of make sure on this one. So, yep. How many of you in here that know about the Rubik's Cube? I hope everybody in the audience should know it, hopefully. Okay. So the notion of God number is pretty much like how many steps you need, minimum step that you need to get to the solved position from any position. So I mean, the regular Rubik's Cubes is already solved at like in 2010 by Thomas, what Thomas here, okay, and then he say, yeah, 20 no matter what happening. But here is a kicker. It requires 35 CPU years. That's a lot of power, which is Google provide for him to finish the solve. The God number for 2x2, which is what we call a pocket cube, is 11. Okay, that's it's not that much on this part, but however, it's still take a little bit of time on this part. So yes, yeah, you're probably gonna ask, hey, are we gonna try to kind of do something like this, which is, by the way, 4x4x4, still not quite sure that happening. Yeah, we don't have 35 CPU year, but can we do a little bit simpler problem? So what happening here, instead of having all 6 color, what happened if you have only 2 color? Okay, there is a 2 type of coloring. This is one way that you can color the 3x3x3 and say, hey, what is God number of this thing? Or even better, how many hard part is position? Oh, can we kind of tell a bit more what we call a group structure on this part? We can have a lot more question on that one. I would, and I'm pretty sure that we are not going to start with 3x3x3 because still many of them still going to use a lot of computer time. We're going to start 2x2x2 and see where we get. Now we also can ask what happened instead of having 2 color, what happened if I have 3 color? Right, so, or actually not only like not okay, sorry, having 2 color, but not just that, every have 3, right? 3 side have 1 color, 3 side have the other. But what happened if you have one side have 5 color and the other one is have 1 color? Those type of variation you can talk about, which is for me is pretty interesting in this part. Okay, and for the small one is you can, I mean, I think you might be able to almost count it by hand, but computer search probably be good. I mean, if you're bored, there is a lot more medical toy here that we can go through. If you kind of like more interesting on this part, so technically it's pretty much countless question and countless type of problem here. And honestly, I have most of them here. Like I think this one here in my hand is probably the easiest puzzle. It's easier than 2x2x2. So we can use those as springboard up. And that's pretty much about my project in general. I know it's not quite number theory-ish, but there is some small number theory inside. All right. I mean, the whole goal is, can we reduce down the big calculation to, or using symmetry to do it? All right. Okay, I'm turning back to Professor Miller here. I think
I am here, thank you. I was just trying to quickly grab some cubes, but unfortunately one of them got shuffled up in my, but anyways, let's see. Is this visible to people? No, it's my video seems to be
I
off.
have the whole box here.
Yeah. So yeah, this one.
Yeah.
It-
It, honestly,
there
I
you go.
leave.
Okay, there you go.
Oh,
So
nice.
so this one looks really bad. It looks like it has 12 sides. It's really the same as a 2 by 2 by 2 cube, but the coloring is meant to fool you. This is another one of my favorite cubes. You know, the sides look like 2 by 3. And the tops and the bottom look a little bit different. This is actually almost the same as the standard 3 by 3 if you hold it at a 60-degree angle. And now here is your side that's your 3 by 3 by 3. So for a lot of these cubes, just as a fun fact, the shapes are designed to mislead you. And to me, this is a great way of looking at modern mathematics. Your job is to find, there's so many equivalent things out there. Which is the one that's going to be tractable for you? How can you recognize that this is similar to something that you know? So we've got about 2 minutes in case anybody in the audience has any questions. Okay,
I have a question.
Yes.
How much like coding experience would be expected for the various projects?
So no coding experience is expected, but if you know how to code, then that means that you can help the project explore certain things. So for example, for the M&M game, you don't need significant coding to write a very simple simulation to do some kind of random walk and investigate what's going on. I have some lectures and some templates that I have prepared on Mathematica. I find that it's a very friendly environment to use if you haven't programmed too much, but whatever you can program in is fine. The more programming skills you have, the more ability you have to look at some things. But for a lot of what we're doing, basic programming is all that you need. For the cube project, what would you say?
For the cube project wise is, yeah, if programming would be great because we definitely need to do a lot of kind of search or kind of computation wise, but it's not required because sometimes you can come up with some kind of like helping with the symmetry or what is a way to think of how we reduce the calculation understanding. So yes, I would love to have some people that know how to code, but we also do have some code already that you can do that provide by Thomas on that one. So
Yeah, thank you. Other questions?
I had a question.
Yes.
So I don't have a huge background in probability, but I do have a background in number theory. Is that enough?
I mean, for most of these problems, I don't think you need much of a background in number theory or probability. Just your elementary concepts, I think, will be enough to start. And then as you get interested, you might have to, go to, some textbooks, some online articles. I've got plenty of things posted. I've taught number theory, probability. All my lectures are online. And just read some of the basics if you haven't seen them before. So if you haven't seen the concept of the mean or the standard deviation, you need to brush up on that. For some other things, you might want to know some basic combinatorics. You might want to know some things about generating functions. And if you haven't seen those, again, those are things that are not too bad to brush up on. A lot of it is trying to figure out what's a good question to ask.
yeah. We have some question on there say what kind of software of coding become a big part of the project. Anything you feel like. If you can make it, that's great. If you can use Python, great. If you use Mathematica, great.
So I have a question.
All right, last question, then we need to go. Yes.
So about the M&M question, so what's a potential problem we need to consider during the project? Like, what's like a question to solve to
Were you here at the very beginning?
the M&M question, the M&M project?
Were you here for the beginning of the talk?
Yeah, I'm here. Yeah.
Okay, good, because we listed several problems and those will be on the slides. Yeah, we said, what if you now have multiple coins? What if you have coins of different denominations? What if some coins have negative values?
Oh, okay.
So there's lots of things you can do.
Okay, thank you.
Okay, have a good day all. We need to go because we need to keep it because I think there might be something at 12. So have a good day.
Yep.
Thank you. Have a good one.
Good.